Okay, let me get started. So my topic is understanding portability of automotive workload, a case study with a points to image kernel in SQL on heterogeneous computing platforms. And this research, first of all, I would like to thank the reviewers for their comments and suggestions. And this work is use the resources at experimental computing lab in our lab, and is supported by the DOE ASCA. So CUDA is an advanced program model widely used by for programming NVIDIA GPUs. In contrast, SQL built upon OpenCL and extend with C++ features is a programming model for heterogeneous computing across vendors' platforms. Studies have shown that achieving performance portability using SQL is non-trivial for application in high-performance computing. So in this work, we study whether SQL can be applied to an automotive benchmark and attempt to obtain a better understanding of portability of this emerging workload with SQL on heterogeneous computing platforms. The image shows three major implementations of the SQL standards. In this work, I evaluated the performance of the benchmarks using the Intel DPC++ compiler. It supports the execution of a SQL program on vendors' hardware. I learned that people are concerned about the growth of SQL. I couldn't predict the life of SQL, but this gives us some opportunity to study SQL. The benchmark comes from an open source benchmark suite comprising computationally intensive routines from automotive applications with parallel implementation in different programming models. In computer vision, three-dimensional points are often called object points, and the 2D image points are called image points. The points to image benchmark projects a point cloud to a 2D view with image transformation and distortions correction. A point cloud contains many independent points that can be projected at the same time. Hence, the benchmark is suitable for parallel execution. A race condition where multiple points are projected to the same view is addressed by atomic functions supported by the program models. They enable concurrent memory accesses without introducing data rates. Hence, updates to memory location do not overlap, but the order is not deterministic. While atomic operations constrain the performance of the kernel, reasonable performance speed up can be over serial projection can still be achieved. In practice, 3D points are often expressed in a word coordinate frame. To relate the word frame with the camera coordinate frame, the extrinsic transformation composed of a rotation and a translation is applied to each point at first in the benchmark. Next, the benchmark applies distortion correction to the position of each point. The model of the distortion is the one used in camera calibration with the Open Computer Vision Library. After distortion correction, the coordinate of each point is transformed with a camera matrix The matrix contains the parameters specific to a camera, including camera, focal length, and optical centers expressed in pixel coordinates. After transformation, the non-integer coordinates are converted to integer coordinates, and the minimum distance is computed atomically with the linear coordinates of each pixel within the 2D image. And due to the time constraint, I will skip the description of the benchmark in SQL. So here is a summary of the optimization I try to apply to the benchmark for improving the efficiency of the kernel execution. The base address to clock point for each thread is computed with pointer castings. The casting can be optimized away with the knowledge that the size of a single precision floating point number is 4 bytes in memory. For the extrinsic transformation, we can manually enroll the nested loops where the trip counts are 3, while a compiler might enroll the loops automatically. Manual enrolling allows us to explicitly expose parallelism in the matrix vector multiplication. Given that the results of some operations are read multiple times in distortion correction, I try to pre-compute the products of these operations for reusing them. In addition, I try to reduce the number of multiplications by factoring out the common expressions associated. When evaluating the SQL kernel targeting an FPGA platform, we found that the atomic operations are not supported with multiple device memories by the compiler. To work around the issue, we rewrite the optimized kernel as a single work item kernel. So here the first the constant values of the coefficients and the matrices are read in the beginning. Then the iteration range of the kernel is represented with a manually coalesced loop bounded by the clock size. Then the number of clock cycles between the launch of successive loop iterations is 1. The return statement, which terminates the execution of a work item in the GPU kernel, is replaced with the condition for a single work item kernel. Finally, the values of the XY are updated before the execution of the next iteration. I evaluate the benchmarks on 4 platforms. The first platform consists of an Intel Xeon CPU and an NVIDIA P100 discrete GPU. The CUDA and the SQL programs are compiled with the support of NVIDIA HPC SDK. And the second platform is an NVIDIA embedded computing platform that consists of an ARM CPU and then integrates NVIDIA Volta GPU. The version of the CUDA compiler is 11.4. The third platform consists of an Intel Xeon CPU and then AMD Radeon 7 discrete GPU. The version of ROCm is 4.5.2. The last platform contains an FPGA card equipped with an Intel Stratus 10 SX280 FPGA. The version of the DPC compiler is 2022.110. The benchmark datasets consist of input and reference data, and we choose the largest dataset, which contains 2,500 test cases for performance evaluation. So the figure on the left shows the execution time in seconds of the CUDA and SQL kernels with respect to the block thread block size on the first platform. The figure on the right shows the offload time of the CUDA and the SQL version with respect to the thread block size on the same platform. The suffix OPT in the figure indicates kernels with the aforementioned optimization, and we observe that the effect of the kernel optimization is not evident across all thread block sizes. However, comparing the kernel and offload time of the CUDA and SQL kernels in the program indicate that the SQL program can achieve performance portability on the platform. Here, the figure on the left shows the execution times in seconds of the CUDA and SQL program with respect to the thread block size on the second platform. From the figure, we observe that the CUDA kernels are on average 30% faster than the SQL kernels. I will explain more in the next few slides. So here I try to obtain a better understanding of the differences of execution time between the two NVIDIA GPU platforms. So by providing the program with a performance profiler and analysis of the profiling results suggest that memory accesses to the unified memory cause the performance drop on the first platform. So the CUDA unified memory is allocated for sharing the kernel results between the host and device in the benchmarks. So on the first platform, the unified memory copies between the CPU and the GPU dominate the execution time. However, on the second platform, unified memory copies are not reported by the profiler because the unified memory is allocated on the same physical memory shared between the CPU and the integrated GPU. So it reduces data transfer overhead between the CPU and the integrated GPUs, as they are directly accessible from both. On the other hand, the offload time on the second platform is significant. This is because I think a lot of time is spent on the execution of CUDA APIs. Here, the figure on the left shows the execution time in seconds of the HIP and the SQL kernels with respect to the thread block on the third platform. And the figure on the right shows the offload time of the HIP and SQL kernels with respect to the block size on the same platform. So comparing the HIP and the SQL kernel indicate that the HIP kernels are 8% to 16% faster than the SQL kernels. So why is that? So I try to analyze the assembly instruction of the CUDA and SQL kernel for a better understanding of the performance gap. So I find that for the floating point atomic main functions invoked in the kernel, the SQL compiler outlines the function and maps the atomic operation to an atomic compare and swap instruction in the instruction set architecture, PTX instruction set architecture. However, the CUDA compiler can inline the function and generates an efficient atomic main function for hardware execution. And analysis of the assembly instruction shows the HIP compiler can also generate an efficient and hardware efficient atomic underscore estimating instruction, while the SQL compiler produces an atomic compare and swap instruction for the atomic function. So table shows the total number of for double precision floating point operations instruction of type add, multiply, divide, reciprocal, and fuse and multiply. and add in the assembly codes generated from the CUDA heap and the SQL kernels for the GPUs. So it shows that the kernel optimization can reduce the number of add, multiply, and FMA operations of the CUDA kernels on the two NVIDIA GPU platform. However, its impact on the instruction count of the heap and SQL kernel is negligible. So the results imply that the compiler may automatically apply kernel optimization to some extent across the target platforms. This table lists the FPGA resource utilization, maximum clock frequency of the kernel implementation, and the kernel then the total kernel time in seconds with respect to loop and roll factor UF. So the utilization covers all resources, including overhead of FPGA, board support package, kernel, memory interface, and its structure. So we find out when the enroll factor UF is 16, results are not available because of insufficient logic array blocks reported by the fitters. This implies that implementing double precision floating point operation on the FPGA is not efficient in resource usage. The execution time of the optimized kernel, which is OPT in the table, is approximately 3.3 seconds, which is approximately 8.6x faster than the baseline. It also reduced the RAM usage and increased the maximum clock frequency. So this is because the optimization allowed the compiler to generate an efficient memory interface and pipeline data paths. On the other hand, the increasing kernel time with respect to the enroll factor indicates that there's no performance gain with the compiler enrolling the outermost loop. So compared to the fastest GPU kernel, the FPGA kernel is approximately 6x slower. There are a few factors that lead to the low performance on the FPGA. So the benchmarks intensive with double precision floating point operations, mapping these operations to the FPGA is less efficient in terms of the resource usage and the latency than the implementation of the single precision floating point operations. And though the maximum clock frequency of the kernel on the FPGA has increased, it is still much lower than the GPU clock rate, which is around 1.3 gigahertz to 1.8 gigahertz. Additionally, the compiler is not effective in exporting data parallelisms through loop enrolling. Finally, the experiments show that the portability of the benchmarks depends on the characteristics of the target platforms and the maturity of toolchains. Our kernel optimization can assist the compiler to reduce the number of floating point instructions executed by the CUDA kernels on the NVIDIA GPU and improve kernel performance on an FPGA, generating more efficient atomic instruction by the SQL compiler will improve performance portability of the SQL kernel on the GPU. The performance of atomic operations is often critical to the performance of an application. Due to the limitation of the FPGA toolchain, the SQL kernel targeting a GPU needs to be rewritten for an FPGA. Implementing double precision floating point operation on an FPGA is not efficient during resource usage and the latency. And the maximum clock frequency of the FPGA kernel is much lower than the GPU clock rate. And the compiler cannot compensate a low clock frequency by exporting more data parallels and by loop enrolling. Thank you. This is the end of my talk. Let me stop here.
Which SQL implementation did you use on the GPU platforms?
Sorry, I couldn't.
Zheming, you cannot hear the question?
Yeah, what is the question? Sorry.
Can you come over here? Yeah. Directly ask.
Hi, thanks for the talk.
No problem.
What was the SQL implementation used on the GPU platforms, like on the Jetson platform, for example?
Which platform? Sorry, can you say that again?
On all the GPU platforms, which SQL implementation did you use there?
Oh, it's the Intel DPC++.
Okay, thank you.
No problem.
Any other questions? And let me quickly ask one more question. So you tested with some automotive benchmarks. Why automotive? Is there any specialties over there, or your like methodologies that you tested for the portability can be used for some other type of workloads as well?
I think that one thing is because one of the motivation I described in the paper is that this is an emerging workload. So, and the original author of the workload also suggests that an evaluation of the workload using a program model like SQL for evaluation. So that's the idea. The other is, I think, is the atomic operations, and I learned that some applications their performance is bounded by the performance of atomic operations. For example, I think currently SQL has added the support of hardware floating-point atomic operations for AMD GPU. So I think which means that now if we run some HIP programs and SQL programs on an AMD GPU, we can observe I think a similar performance. Previously, without the support of these floating-point atomic operations, native floating-point operations, the performance gap between a HIP program and a SQL program is significant.
Okay, thank you so much.
No problem.